Okay, last time we just started some basics about the functions. Especially we talked about piecewise defined functions. Um, you know, how do we make sure the function is well defined? Sometimes it's not so obvious, and you have to check the conditions carefully, especially when you can input uh, different numbers uh, belonging to the same uh, equivalence class. For example, they actually present the same argument. You can have different representations for the same argument. Then, if its function is well defined, then you should only get one output. And this is the way to check whether the function is well defined or not. And we did one example, not just one, but a couple of examples. Especially the one with the congruence classes. You know, but um, uh, congruence relation is important part in our class, in both classes actually. So we need to be clear, what it means when the function is defined on the equivalence class and what the output is in different in different types or with different divisors, right? Or modulus. Anyway, we're going to continue with this topic about functions. We talk about a lot of things about functions before in algebra when you learned intermediate algebra or pre-cal. But we are looking at the same thing in different views in a more general, abstract way. We define everything in sets. Remember, if you think about it, the rules, the sets, and all the pairs. So this is the unit of functions, and the second section is the injective and the surjective functions. This is the 25th topic in the book, but it's section 2 in our unit. So we're going to start from injective functions. We know a function has to be defined such that each element in the domain can only be paired with a unique element in the codomain. But it doesn't say anything about the elements in the codomain. All right, so we have two sets, A and B. A is the domain and B is the codomain. So you map every element in the domain into the codomain. And you can map several, even all of the elements in the domain into a single element in the codomain. And that's perfectly fine in the definition of functions. And also, not all the elements in the codomain have to have a pre-image from the domain under the map. Okay. So, but in case both are true, in case, each element in the codomain has a pre-image from the domain under the map, and then we call it onto, right? And we also have another situation where each element in the domain can be only paired by a different element in the codomain. That's called a one-to-one. And then we have these two cases, and we all know we learned before, but we also call one-to-one as injective and onto as subjective. So these are all different terms. So we're going to discuss each of those separately. We start from injective functions. So let's start from the general definition of function. You can easily determine whether a function, a relation is a function from the vertical line test. If you draw the graph of the relation on the xy plane and you draw a vertical line, then the condition is the vertical line can only intersect the graph at most one point. If that's the case, then we know the graph represents a function, otherwise it's not. So that's called the vertical line test. The vertical line test is used to check whether a relation is a function or not. And there's another test called the horizontal line test, and you probably know it. That's to determine whether a function is one-to-one or not. Namely, if the curve intersects any horizontal line at most one point, then we call the function is one-to-one. Otherwise, it's not one-to-one, and that's easy to understand. If you, for example, if you have two intersections of the curve with a horizontal line, that means for each of the y value, you have two different x values paired with it. So that's not one-to-one, that's two-to-one, right? So the horizontal line test checks whether the function is one-to-one or not. Okay. It's checking the one-to-one, but not the one-to-one correspondence. There's a difference between those two terms. Okay. You can only check whether the function is one-to-one, but it's not the same as one-to-one correspondence. So based on that, we can define the inject functions as follows. So letter A, letter F, from A to B, the functions of A and B are two sets. A is called domain, B is called the codomain, as we know that. So F is a function, or we can call it mapping, the same thing. So then we say F is injective if distinct elements of A are mapped by F to distinct elements of B. Right? In other words, for any arbitrary A1, A2 in the domain A, if A1 is not equal to A2, then F of A1 is not equal to F of A2. All right, so different elements in the domain map to different elements in the codomain. And usually, a lot of times when we want to try to prove a function is one-to-one, it's easy to do it by using the contrapositive instead of working with inequalities. But sometimes we do work with inequalities, as you're going to see an example. So the contrapositive statement will be, again, we would pick up any two elements A1, A2 in the domain A, and then you assume that the function values f of A1 and f of 2 the same, and then if the function is one-to-one, then you can conclude that A1 is equal to A2. You should be able to show that A1 is equal to A2, and we all know that. Okay, so I'm not going to spend too much time on it. Okay, so the term one-to-one, that meaning each element of B is the image of at most one element from A. Okay, so one-to-one. It's not it's not it's saying that that's not referred to the fact that the function takes each individual element of A to one element of B. That's the basic requirement for the definition of a function. One-to-one, it means you can map any element in the domain to distinct element in the codomain. So in other words, for each B in the codomain B, either there is a unique element A in A subset F of A equal to B, or there's no element in A subset that maps to B. So that means you may have the situation that some elements in the codomain cannot be obtained from the mapping on the domain. All right. Okay, so in other words, a function f from A to B is injected exactly when each B in the codomain B is the second coordinate of at most one ordered pair in F. Okay, so you either is the second coordinate of one ordered pair or no ordered pair. So some elements in the codomain do not have pre-image, and that's still one-to-one, okay, as we know. All right. So let's just start from simple example. Suppose we have two sets, A and B, the domain and the codomain, respectively. So A has three elements, 1, 2, and 3, and B has four elements, 1, 2, 3, 4. So we define a function, f from A to B by their following order pairs. All the functions can be written in the form of order pairs, the set of order pairs, as you know. So 1 maps to 4, 2 maps to 3, and 3 maps to 1. So you can see different numbers in set A map to different elements in set B. All right, and actually the number 2 in the set B has no pre-image. And the function is still one-to-one, all right? So distinct elements of A map to distinct elements in B, in other words. So this function is one-to-one, and it's always helpful to draw diagrams like this. You just draw the two sets with the numbers marked in each set, and then you draw the lines from the pre-image to the image respectively. So we got 3 maps to 1, 2 maps to 3, and 1 maps to 4. So obviously this function is one-to-one, and it is a function. Okay, you can all see from here. there's only one arrow going out from each element in set A. And the one-to-one property essentially means there's only one arrow coming in to each element, at most one element coming into each element in set B from set A. So, all right. So there's never more than one arrow pointing at an element that would be in the diagram. Okay, let's look at one more example. So again, the two sets A and B are the same, but we define another function from A to B by again 3 other pairs. The pair 1, 4, pair of 2, 3, and pair of 3, 3. So obviously the number 3 in the codomain B has 2 pre-images. So that's not one-to-one. And you can also draw the graph. You can easily see, the number 3 in set B has 2 pre-images. All right. That's not the injective. Okay. The next example is a function from R to R defined by fx equal to x plus 1. And this is a injective function. Also, you can easily check it by the horizontal line test. Remember, we can use horizontal line test to check whether the function is one-to-one. Or we can easily prove it. So, you just pick up two values of x1, x2, and suppose fx1 equals fx2, then you should be able to prove that x1 is the same as x2. So, and that's easy to do, fx equal to 1 equal to fx2 means 2x1 plus 1 equal to 2x2 plus 1. If you plug in x1 and x2 in the function, in the formula, and then after subtracting 1 and divide by 2, you end up with x1 equal to x2. So that means f is injectable. Pretty straight. Another example, again, is from R to R. Now, this time we define a function f equal to x squared. This is a quadratic function, or if you plot in the xy plane, that will give you a parabola. And this is not a one-to-one. It does not pass through the horizontal line test. You get 2 intersections with the parabola when y is greater than 0. Well, obviously, if x is equal to 1, 1 squared is 1, and if x equal to -1, -1 squared is also 1. So we got the same y value is different the x value. So it's not one-to-one, all right? Or not injected. Okay, now if we change this function a little bit, if we change the domain from the all real numbers to non-negative numbers. Remember, the previous function is defined from R to R. Now we just change the domain a little bit from R to non-negative numbers. Then it becomes one-to-one function or injective. And if we draw the graph, it does pass through the horizontal line test, because this time you only have the right hand half of the curve when you restrict the domain to be non-negative, right? You don't have the left hand half of the curve or the parabola. But you can easily prove this is one-to-one, Again, just assume x1, x2, and pick up any two arbitrary numbers, x1, x2 in the domain, and assume fx1 equal to fx2. So that means x1 squared equal to x2 squared. And, then just like you solving equations, you put everything on one side. So subtract the x squared, 2 squared on both sides. For example, you get x1 squared minus x2 squared equal to 0 and factor it. Okay. That's how you solve equations, right? So then you get x1 minus x2 times x1 plus x2. Okay. So then we got the two situations. So either x1 minus x2 is 0, or x plus 2, x1 plus x2 equal to 0. So we have two cases. Case 1 is x1 plus x2 equal to 0. All right, but because all the x are non-negative, so the minimum value for x1, x2 are 0. And if you want the sum to be 0, then both of them have to be 0, right? You cannot have any of those values to be positive because the other number is not negative. So both x1 and x2 have to be 0. So in this case, we got the x1 equal to x2, right? Actually, they're both 0. But the important thing is x1 is equal to x2. Okay, so that's one case. So it is one-to-one in this case. The other case is x1 minus x2 equals 0. Obviously, that also means x1 equal to x2. So in all situations, x1 has to be equal to x2. So we just prove the function is injective. Okay. Let's do another example. So this time we define a function, a rational function x minus 1 or x minus 2. And we have to be very careful about the domain and the codomain. Okay. Well, especially the domain. Okay. So obviously you cannot use 2 for the x. So the domain of the function is all real numbers except 2. All right. But you can easily find also that the function value can never be 1. Okay, remember, why do we take off 1 from the codomain? So suppose this function value is 1. So so if f of a were equal to 1, then we have this equation a minus 1 over a minus 2 equal to 1. Then you can easily solve this equation. You multiply a minus 2 on both sides. So you get a minus 1 equal to a minus 2. Then you get the negative 1 equal to negative 2 if you cancel the a on both sides. And that's not true. So you can never have the situation for f of x equal to 1. So that's why we take off the value 1 from the codomain. Okay, but you don't have to. Okay, for a general function, you don't need everything in the codomain having a pre-image in the domain. Okay, but we take out the 1 from the codomain, just to indicate the range in this case. Okay, so how do we prove this function is injective? Again, you just pick up any two numbers from the domain, x1, x2, and so set fx1 equal to fx2. So that means x1 minus 1 over x2, x1 minus 2 equal to x2 minus 1 over x2 minus 2. You remember the function is, x1 over x minus 1 over x minus 2. And this easy to solve. You do the cross multiply. Remember, whenever you have a what? Equal sign, between two fractions, you do the cross multiply. I don't remember what it's called. Proportion, I think it's called proportion. Okay. And a lot of people just get confused about the proportion and the multiplication of fractions. When you multiply two fractions, you just multiply top by top and bottom by bottom. But if you have a proportion, you do the cross multiply. So don't get confused. So then we get x1 minus 1 times x2 minus 2 equals x1 minus 2 times x2 minus 1, and then you follow both sides easily. So x1 times x2 minus 2x1 minus 1x2, or just x2, and plus 2. -1 times -2 is plus 2. On the left hand, similarly, you get x2, x1 on the right, which is same as x1, x2, and -2, x2, -1, x1, or -x1, and the plus 2 again. So then you cancel x1 times x2 and cancel the 2, and then you just arrange the terms and combine like terms. You just put everything on one side. For example, what you end up with will be x1 equal to x2. Okay, so then this shows that the function is injective. Okay, again. All right, so let's do another example, which is this time is a little different. So suppose we define a function from f from z to z by this formula, by this. So this is a piecewise defined function. So f of n equal to n plus 1 if n is greater than or equal to 0, and f of n is equal to n if n is less than 0. We want to show that f is injective. So we can do the same thing as we did before. You can pick up two arbitrary integers, and 1, 2, and set f of n1 equal to f of n2. Then you should be able to conclude that n1 is the same as n2. But it turns out it's even a little easier if you do it the other way. Namely, you just let two different integers. You start from two different integers from the domain. Okay, and then you show that f of n1 will not be f of n2, or a or b in this case. So we're doing in the other way. If you try to do the way we did as the other examples, you pretty much will go through all similar arguments and even a little more steps. So it turns out doing, the inequality is a little simpler. So let's just pick up two integers, a and b, from the domain Z, and assume they're not the same. Okay. And then because the function is piecewise defined, that automatically tell us that we have to deal with different situations. We have to discuss the cases one by one. You have to separate the cases of positive and negative, because A and B both can be positive and negative. So, to make the discussion clear, then, you have to split different cases. And there are only three different cases, in terms of positive and negative. Either A and B both positive, or A and B are both negative, or one of the two numbers is positive and the other is negative. So there are only three cases. So let's just go through these three cases one by one. So suppose both A and B are non-negative. Okay. So we're using the non-negative instead of positive because that's how the function is defined piecewisely. Okay, if both A and B are non-negative, then you're going to use the top formula. So f of A equal to A plus 1, and f of B equals B plus 1 also, right? So then we need to show A plus 1 would not be equal to B plus 1 because, that's what that's our goal. We assume A not equal to B, then we should conclude that f of A not equal to f of B. And that's actually the case because A is not equal to B, so A plus 1 is not equal to B plus 1, obviously. So that's the first case, and the second case is when both A and B are negative. Okay. Then f of A equal to A and f of B equal to B, according to the definition of the function. So f of A not equal to B become not equal to f of B becomes A not equal to B, right? And that's obvious because that's what we started. So the second case is true, and the third case is when one is negative and the other is non-negative. Okay, we only need to prove, for example, when A is negative, B is non-negative, and the other case of B negative and A non-negative is pretty much the same. So let's just assume A is negative and B is non-negative. A less than 0 and B greater than or equal to 0. So without loss of generality, we usually use this argument quite a lot. So then we have to be careful about the function values of f of A and f of B, because they are defined differently in function f when they're negative or not. So, and because A is negative, so then f of A will be equal to A, right? Okay, so, and because B is non-negative, so then B is not negative, right? So then we're going to use the top formula. So f of B equal to B plus 1. Okay. And we want to show that A is not equal to B plus 1. That's obvious because A is negative. That's how we started. And B, A is not negative. So B plus 1 will be positive. So A is negative and B plus 1 is positive. So they cannot be equal. So once again, f A not equal to f of B. All right. So so we have proved all the cases that when A is not equal to B, f of A will not be equal to f of B. So that means this function is one-to-one or injective. So this is the one thing that we should be aware that when we deal with piecewise defined functions, we usually need to separate the cases based on the definition of the function, and that's almost true every time. So this is about the inject functions, I guess. Okay, I guess I will not talk about strategic functions. I'll leave it to the next class on Wednesday. We'll not be able to do much about strategic functions today. So let's just stop here. I mean, the important thing here is actually, how to deal with piecewise defined functions. Okay, this is always something that brings up a lot of trouble. Any questions at this point?
No, no questions.
Yeah, I think this is pretty straightforward since you already learned before. But we just did some examples on how to prove the function is one-to-one or injective. So this is the thing that you should learn. You can do it in different ways. You can usually you're gonna assume the two functions values are the same and then prove the two x values have to be the same. But sometimes it's actually easier to do it in the other method. If you set 2x value not equal, then you show the two function values are not the same. So